Today we will be talking about uniform circular motion. Uniform circular motion is motion of an object traveling at a constant speed in a circular path. So you got a kid has a model airplane attached to a string, and he has it flying around in a circle. It's going at constant speed, but yet it's not a constant velocity, and the reason is, even though the speed is constant, he's constantly changing direction, so the velocity is not constant. The speed is, but the velocity is not. Okay, let's derive an equation for the speed of an object moving in uniform circular motion. There we got the kid with the plane again, and we know that speed is equal to distance over time. So what is the time it takes to go around a circle called? By definition, that's called the period. That's how long it takes to go around one time. And we know the circumference around a circle is really just the distance. So we can replace distance with circumference and time with the period. All right, let's try a problem with this. The wheel of a car has a radius of 0.29 meters and is being rotated at 830 revolutions per minute. Now that's not a period. Okay, that's how many times it's happening per minute. So we need to change this into how long it takes one to happen, not how many happen per unit time. We want to determine the speed at which the outer edge of the wheel is moving. Okay, so this is revolutions per minute. We really want to find out how many minutes per revolution. So I just took the reciprocal. And then I need to get that into seconds. So I took this period, 1.2 times 10 to the negative third, and I have a conversion factor turning minutes into seconds. And one revolution would take 0.072 seconds. Then I plug into the little equation, and I can find out how fast the outer edge is actually moving. That would be like if you took the outer edge of the tire, how many meters per second it would cover. Okay. All right, in uniform circular motion, the speed is constant, but the direction is not constant. So let's take an example. We have an object going around in a circular motion. At time 0, it would want to fly off on a tangent at this point due to Newton's first law. If the string broke, it would fly off a tangent. So that this radius is always perpendicular to the velocity vector it wants to fly off at. And sometime t later, it has the same magnitude of velocity, but now it's pointing in a different direction. Notice once again this is 90 degrees because it always wants to fly off on a tangent. So these velocity vectors are always perpendicular to the radius. The velocity at time t can be moved, as shown in this next diagram, as long as we don't change the angle or the magnitude. So what I did is I took this here and I just moved it all the way up here. Now you might be thinking, why did I do that? The reason I did it is I'm deriving an equation for centripetal acceleration, which we'll get there in a moment. Okay? All right. Notice that these two are perpendicular, which means that this line here, the pinkish line, is perpendicular to this line, and this red line is perpendicular to this line, CP. So with that in mind, if this is perpendicular here, 90 degrees, then alpha plus beta must be 90 degrees, all right? And since alpha, theta, and this angle right here must form a triangle, here's a triangle, then alpha plus theta plus this angle must be equal to 180 degrees. And since this angle here is 90, then alpha and theta must equal 90 as well. So why am I saying all this? I want to prove that beta and theta have to be the same. Because if alpha and beta are 90 and alpha and theta are 90, then beta and theta must be equal to each other. All right, so why am I doing this? Because I'm going to make two similar triangles. I'm going to make a similar triangle of these two velocity vectors, So this is initial velocity, this is the final velocity, and I'm also going to make a triangle of the displacement from here to here. And you'll see that in the next slide. Okay, and here's the two diagrams I was talking about. The first depicts a diagram of the change of velocity from positions O to P. So this was the velocity at O, and this was the velocity at P, and this was a change of velocity. And this is a diagram of the displacement from O to P. It follows this dotted line. And if we think of this as small angles, we could replace this dotted line with a straight line and not really have much error, as long as the angle is pretty small. And so how far would that have traveled? It would have traveled at whatever velocity it was moving at for however long it moved at. So this distance equal velocity times time, would be velocity times time. All right, so how can we use this? First of all, you have to realize that they're both similar triangles and they're isosceles. In other words, this angle and this angle are the same, which we proved before, and these two lengths are the same, and these two lengths are the same. So we're going to set up a series of similar triangles and see what happens. All right. Since triangles are similar, we could set the ratios of the sides equal. So what is this actually saying? It's saying that this side here divided by this velocity must be equal to this side here divided by this radius. And through a little bit of algebra, I bring the delta t down to this side and the velocity up to that side. And I know that any change of velocity per unit time, is acceleration. I've now derived our acceleration equation, our centripetal acceleration equation, where the velocity tangential, that's the velocity it would be going off at on a tangent, squared divided by the radius is equal to the centripetal acceleration. All right, this next slide here explains a little bit about what direction this acceleration is acting in. Okay, so we know that acceleration centripetal is equal to v squared over r. And this is a different diagram. Here you have an initial velocity at point A, a final velocity at point B, and what I'm trying to do is find out what the change in velocity is. And I know that change of velocity is final minus the initial, or final plus a negative initial. Let's see if you can understand that. Final minus the initial would be equal to the final plus a negative initial. All right, so here I got the final velocity, and all I'm doing is adding the initial, but in the opposite direction. That would be the negative v initial. And if you look at that, this, then this, is the same thing as this. So delta v, in this case, points toward the center of the circle, proving that centripetal acceleration acts towards the center of the circle. So the acceleration equation we just derived, we can prove now that it acts towards the center of the circle.